So in the earlier examples, we were only dealing with half the system. We were either dealing with metal or water, but not both of them together. We're about to move it into the situation where it's both of them together. So let's have our container. There's something hot in water. Remember again that the hot thing is going to have the energy going out. Remember, no energy is lost or gained. The total quantity of energy is the same. But just remember that the out energy is negative Q, and it's going to the water, which is positive Q. So we have Q equals Q. Just remember that Q hot is always stated as negative. So what this is going to have happen is that it's going to be a negative. See, look at this. You're going to have a negative because Q is always stated as being a negative number for the hot thing. A negative times a negative is how you end up with a positive cool. And that's how we say that you haven't lost or gained any energy. It's just going from one substance to the other. It makes more sense just thinking about it than looking at the math for it in some way. So just notice we have the subscripts for the hot and the cold side. The hot is what gets the negative. It's really easy to drop that negative too. So if your answer doesn't make sense, go back and check and see if you've dropped it. So we've got the hot side of the equation with the negative, and we have the cool side with on the positive side. So I'll work an example problem, and then I'll let you guys work more example problems. It's kind of more of the same, but you need to really keep up with your numbers. And there's one other detail we need to make sure that you're remembering, and it has to do with temperature at equilibrium. This is how we set up our numbers before, but we don't need the Q because the Q's are being set equal to each other. So we're dealing with the lead first, 34.6 grams of lead. Notice the C is given. 0.449 joules per gram degree Celsius. And then our temperature change, our initial, because it says it's at 104.6 degrees Celsius. And this is what happens. Now read the problem carefully. The temperature at equilibrium is 29.7 degrees Celsius. That is the final temperature of the metal, but it's also the final temperature of the water because remember, they continue to exchange heat until they are the same temperature. This is going to be true for all of these styles of problems. One of the temperature numbers is going to apply for both parts of the equation. All right, so now we're going to put it in our T final minus our T initial. So our final temperature of the metal is 29.7 degrees Celsius, and we're subtracting the 104.6. And you can probably already see we're going to end up with a negative. That's okay. That's why we have a negative in the equation. So our answer is going to be negative 74.9. That's, of course, degrees Celsius. Now we are switching to the unknown liquids information. So it says that the mass is 30.4 grams, so we're going to be writing that in. Now it asks for the specific heat capacity of the liquid. That's our question mark. And our delta T is final minus initial. And remember, we already said this. The final temperature of the water is at 29.7. And then the initial is in the problem, 22.4. Now you just go ahead and do the math right here. It's going to come out to be 7.3. Notice it needs to be rounded to tenths position. Now we're going to plug it into those two equations. Don't forget the negative. So we're going to write down negative 34.6 times 0.449. That's the specific heat. Don't forget the units. Times your change of temperature, 74.9 degrees Celsius. Notice that that was a negative. So look, our negative times negative cancels. It'll become positive. That's what we want to have happen. On the right-hand side, 30.4 times C times 7.3. Divide both sides so that we can get the C by itself. 30.4 times 7.3. Cancel out what's the same. So we're left with C equals, it equals 1.49 joules per gram degrees Celsius. So we need to watch our sig figs on this. If you look back through, remember our change of temperature resulted in something with only 2 sig figs. So we need to change this so that it only has 2 sig figs. So the right answer is going to be 1.5 joules per gram degrees Celsius.